As a point of logistics, please do not use the Zoom chat. It's very annoying for me to deal with that. You have the Slack link, so please post questions on Slack. I have that on a second monitor. If you need to post code snippets on Slack and you've never done that, use the backtick. If you make 3 backticks, then you can write a whole code block. So Slack is very convenient. So post questions there, and I'll get started with lecturing. I'm sharing my second monitor. Okay. So first of all, I posted a couple of links in the Slack channel. They are at the top of your screen. So those point to my The Art of HPC website, which hosts my, by now, 4 HPC textbooks. Download them and read them when you feel like it. Volume 3, Introduction to Scientific Programming, covers modern C++ and Fortran. And the first button is the textbook download link, and the second button is a whole bunch of lecture slides, and the Slack channel has the explicit link for the course materials for this course. Okay, so this is where the actual lecture starts. Good morning, C++ for C programmers. So I'm assuming that the audience is already a reasonably well-versed C programmer. You know how to tinker with ampersands and stars, malloc arrays and all that. And you want to know what this object-oriented stuff is about. Well, there's more to C++ than just objects and classes. I'm going to teach you new things, and I'm going to unteach you things that you should no longer use, even though they are possible. So stop writing C. C++ is a more structured and safer variant of C. So you can do more in C++, and you can do the same things in a better way. So there are very few reasons not to switch from C to C++ or to use C++ for your new code that you're developing. Now, C++ almost has C as a subset. There are some differences at the edges, but basically most of what you can write in C, you can write in C++. But there are a number of things that you are used to writing in C that you should no longer use in C++. If you want to see a entertaining and informative lecture about this, there is a YouTube link to a lecture by Kate Gregory, which is called Stop Teaching C, if I remember. And that makes that point very well, that you should not consider C++ as a C with a cherry on top. Certain parts from C should no longer be taught and used. Okay, so what we're doing today is mostly object-oriented programming and the new array mechanisms in C++. So no longer malloc and creating arrays with square brackets. C++ has better mechanisms. And so that's what we're doing today. And then next week, we'll hit a whole slew of shorter topics of new things that exist only in C++ and that can make life really easy for you. So I'm assuming that you know how to write C loops and functions, that you understand what structures and pointers are, and based on that, I'm going to show how things are done in C++. I am going to break at a number of points for exercises. It is really a good idea to exercise your skills immediately. If you get stuck, you can ask me right then and there by posting a question in Slack or so. Just listening to this lecture does not give you any practical skills. So there will be a couple of exercises that I would like you to spend 5 or 10 minutes on. Besides, that gives you a break from having to pay attention to me all the time. Oh yes, for that, on the website that I pointed out, there is a link to the public source repository, which has some skeletons for the exercises. Okay. Right, so here's my textbook. Okay, so first of all, C++ has undergoes pretty quick development. Since 2011, a new standard has come out every 3 years. And unfortunately, there are quite some books and tutorials online that don't acknowledge this fact and that teach really pre-modern C++. So in this lecture, I will be using C++ 17 and occasionally 20. And so some of the examples will not compile with the default compiler settings. And so you need to tell the compiler that you're using a modern standard. You can, for instance, alias that in your bash RC or something. So be aware that there are different standards and that I'm using, every compiler has its own default setting for what standard it accepts, and that may not be 17. So you may need to tell the compiler in a settings file or whatever to use the 17, at least by default. If you're writing if you're using CMake to compile, then use the target compile features and tell it that your code is C++ 17. About these standards. So the first official C++ standard was 98, and there was a marginal revision in 2003. This is, you may still find code that is written in C++ 98, but that is really not the best standard anymore. What people consider modern C++ is 11. 11 was a big rewrite, and then 14 and 17 did some minor refinements on that. But basically 11 is the watershed moment. That is modern C++. That is what you should use. C++ 20 added, again, new features, and sometimes this is called postmodern C++. Most compilers nowadays support many of the 20 features, not all of them. And C++ 23 and 26 are under development. I believe C++ 23 is now frozen and compilers are rolling out features. And many of the features of 26 are already known, and some compilers support them. You can download bits of 26 because people have implemented the library features already. But basically, we are doing 17 and maybe 20. So what is not modern C++? Parameter passing with ampersands. If your code calls a function and there is an ampersand in the function call, that is not modern C++. Don't do that. malloc, and maybe you've heard of new, are also not modern C++. Don't do that. unless you're becoming really advanced, and there may be a reason, but basically for now, no mallocs and news. Let me point out some really minor enhancements. There is now an actual Boolean type, so you no longer have to use ints with 1 is true and 0 is false. There is an actual Boolean with values true and false. Single line comments can be done with double slashes. And type defs are often unnecessary by using the using statement, which is a lot more readable. So you can do things like, say, real is float, or sometimes when you get very complicated types, you can use using as an abbreviation for that complicated type. One thing that you should even start using in C is the initializer statement. So it is, I think, bad practice to declare your variable and then use it in a loop. A loop variable should be local to a loop, because that's the only place it has a meaning. And so declare your loop variables in an initializer statement. That is part of C99 and part of C++. So even if you're writing C, please write it this way. Now, C++ has also initializer statements in conditionals and in the switch, but strangely not in the while. So you can declare variables local to a conditional by saying if character C is whatever input statement, and then test on it, and then your variables local to the conditional. That is conceptually cleaner. You can still use printf in C++, but there is a simple way of doing I/O with the C out and for input C in statement. So for an output statement, you write C out and then double chevron strings and variables, and \n for a new line. So that's a very simple way of doing I/O. If you start doing formatted I/O, this gets more complicated. And next week we'll see a completely different mechanism, which is a bit like printf, but better. So for now, in this course, I will use C out just because it's very simple to write. And the better mechanism is actually only part of C++ 20, so I cannot assume that everyone has it. Okay, so your first program, hello world. So in the left code panel, I hope this is big enough to be visible to everyone. Okay. In the left code panel, I'm using C out, but in order to use that, I need two things. I need an include statement, include IO stream, so that is where C out is defined. But even then, I cannot use it immediately because this is part of the standard library, and C++ allows you to have multiple definitions of C out. Maybe you want to write your own, and they can even all be active at the same time. And that is done through a mechanism called namespaces. And so in the left code panel, I'm saying, okay, if you come across a name, try to find it in the standard library namespace. So now, I include IO stream, which defines C out. And I'm telling it to, if you come across an identifier, try to find it first in the standard namespace. And so now I can write cout. Okay, this using namespace standard is great for simple programs, but be aware that it has a number of pitfalls. And so a cleaner way for doing things is to say, okay, I'm including IOStream, and from this, I am only abbreviating standard cout as cout. So that means that every routine that comes out of IOStream, I now separately have to say, use that routine from that header. Using namespace is convenient, but I'll point out later what the problems with it are. So for simple programs, okay. For more serious code bases, use the explicit using standard cout mechanism. Like I said, much of C is included in C++, and in fact, all the things that you hash include, so standardlib.h, standardio.h, you can now include them that way, or you can include CMath, C standard lib. So you can still use the same C headers. CMath is convenient to use, but don't include the C standard lib and C standard IO. They have been replaced by better mechanisms. Still, all the C headers are available through this mechanism. Okay, we come to the first serious topic, functions, and in particular parameter passing. Now, there are a couple of minor topics like that parameters can have default values and polymorphism is possible. But basically, we're going to be talking about parameter passing, which is done very differently in C++ from in C. Okay, how are you going to write your functions? So a first design is data goes into a function, and the function has a returned result. So data goes into the function, and the return statement is the only way that results come out of the function. In this case, parameters are copied into the function, and ultimately you're going to worry about the cost of copying, but they're copied into it, and so this is called, in compiler terms, parameter passing by value. And this whole design of values going into the function and only the return result out is sometimes called functional programming, also known as side effect-free programming. And this is a very clean design, and for philosophical reasons, you should really write this way as much as possible. Now, another design is functions don't return a result, or maybe they only return an error result. So your function returns, say, an int where 0 means success, and any other value means some error or informative condition. And the computed result of the function is, in a metaphorical sense, returned by changing the parameters. So this is called parameter passing by reference. So the parameters are no longer copied into the functions, but you pass a reference to the parameter so that the function can change the value of what it's passed with. So this is how you're used to doing things in C. Now, for C++, there is a different mechanism for this. C++ does not actually have, C does not actually have a pass by reference. What happens is that you pass an address by value. This is not very philosophically clean. So C++ has an actual reference mechanism, which maybe a little confusingly uses an ampersand, but the meaning of the ampersand has changed. Asterisks are out. If you find yourself writing asterisk, you're not writing idiomatically C++. Rule of thumb for now while you're learning things. There are advanced cases. Okay. Enough words. Let's take a look at some code. So ampersands are used not to take an address, but to indicate a reference. And let's first look at references by themselves, not in the context of a function. So I have an integer I, and I have a reference to int ri. And so line 2 means that ri is a reference to I. In C, you would have written int star ri is ampersand I, which means that ri is not a reference, but it's the address. This is different. Ri is a reference to an int, but it acts like an int. It's more like a synonym to the original variable. It's not its address, it's a synonym to it. So on line 3, I'm setting I to 5, and now I'm printing I and Ri. So I've not set Ri, but I print it, and the first line of output is 5,5. Note the cout statement. I print the variable I, the string comma, the variable Ri, and then a new line. Now I multiply I by 2. I print again I and Ri. I get 10,10. So because Ri is a reference to I, meaning a synonym, an alias, its value also has changed. And I can demonstrate that by on line 7, changing the value of Ri. And because I and Ri basically reference the same thing, now if I print I and Ri, I get 7,7. Okay, so a reference is not an address. A reference means the two things refer to the same memory location. So a reference is an alias, a synonym. Okay, this sort of code you will never write. There's not much point to it, but this reference mechanism is going to be used in functions. Let me just point out some of the limitations of references. If I have a float x and I make a float reference xref, that is the way it's done. A reference can only be created immediately bound to the variable. You cannot say create a float, declare that something is a reference, and then refer to it. A reference is completely tied. You cannot redirect it. References and pointers are a little different. References always refer to something because you create them by referring to something. There are no null references like there are null pointers. There is actually a null pointer thingamby, but that's completely different. And references are bound when they're created and they cannot be retargeted. Okay, now how are references used in functions? So void f int ref n. So this is different from C. I declare my function to I declare my function not with an int, not with an int star, but with an int reference. So this means that the function parameter will be a reference to something in the main program or the calling environment. And now if the function does something to n, because the parameter is a reference to what it was called with, it changes what happened in the calling environment. So in the main program, I have an int I pass it into the function, not with an ampersand, but by itself. And then in the function, the parameter n becomes a reference to the int I of the main program, and the function changes n, and then I in the main program has been changed. So this means you no longer have to worry about all the stars and dereferences, which is, to me, the main hurdle in learning C. So this is a cleaner syntax. So let's see this in action. Line 1, I have a function f with a reference to int. So when the function is called, int I becomes a reference to the calling environment. I set it to 5. In the main program, I have a variable, int var. I pass it to f. And then on line 8, when I come out of the function, I print var, and lo and behold, it is 5. Okay, so compare this to how in C you would have the ampersand in the call, not in the function definition. And then in C you would have to dereference that thing, which is confusing and takes a long time to get used to. And even then, when you start tinkering with double, triple stars, it is very confusing. Okay, so this is passed by reference. So I mentioned a couple slides back the design where you have a function that returns some informative result and passes values by the parameters which are by reference. So for instance, you would write a function can read value, which returns the Boolean yes, no, I was able to read. And it returns through the parameter passing mechanism the actual value that was read. So you have a function, you try open a file, and if you can read the file, then you pass the value back and you return back as the Boolean result whether it was possible to open the file. And then in the main program, you say, if I cannot read the value, then I set it to some default value. So this is a sort of design of functions that is not functional programming, and it illustrates the pass by reference mechanism. So the pass by reference, I have now showed you that you use it so that you can alter the variable that was passed into the function. Sometimes you don't want to alter this, and the only reason you're using the reference is that without a reference, you would copy the argument into the function. And if the argument is something big like an array, you may not want to copy it. You want to pass it by reference to save the copying cost, but then you run the danger of maybe inadvertently changing it. So what you come across in a lot of idiomatic C++ programs is const ref. So you have a function and you say, my argument is a const ref, which means it's a reference to whatever it's called with, and so it's not copied, but you declare it to be constant so that you're preventing from inadvertent changes. With an int, there's no point to this. But with more complicated objects, you really want to save on the cost of copying, and so you use a const ref. Okay, exercise. I'm giving you the opportunity to spend 5 minutes with your favorite compiler and show me that you can do this. Write a function swap of two parameters that exchanges the input value. So you have an I and a j, and they have values 1 and 2. And then you call swap ij, and suddenly they have been flipped. Okay. I'll set a timer for about a good 5 minutes. Work on this, and if you have questions, ask in Slack. I will take this opportunity to get a glass of water. I don't know if people have their Slack channel somewhere peeking out from under a window. I just posted a I think I just posted a poll. Lauren, is that visible in Slack?
Let me look real quick. Yep, I see it.
Okay.
We have 6 responses so far.
Yeah. Really? I only see 3. 4.
Oh, weird.
Oh no, you shouldn't look at the 1, 2, 3 in the right column.
Okay,
It's the,
yeah, I see that.
the red 1 and 3. Yeah. Interesting. No Windows users. In the undergraduate class that I teach, the overwhelming majority of students have Windows machines. Sorry. I should censor myself when the recording is on.
That's
I'm going
okay.
to edit this, right?
I'm just waiting to see if anybody else responds on the poll.
How are people doing? Is anyone doing the exercises? If you manage to get it working, could you post your solution in Slack? Use triple backticks and then cut and paste a couple lines of code. Alan, that's a tilde. The backtick is shift tilde. No, it's not shift. Tilde is so you can cut and paste. Yeah. Okay. Yeah. So the yeah, I see 2 people posting the correct solution. Thank you very much. So I assume this is simple enough that I don't have to show the solution, right? So if you feel like doing more exercises, you can do the optional exercise where you write a function is divisible, number, divisor, remainder. And yeah, it does the obvious thing. So if you feel like doing more exercises, here are some suggestions. And if you can later send them to me. And if you want my feedback on it. Someone posted in this. Yeah. Oh, so please don't use the chat. It's annoying for me. I have to click on it and all that. Okay. Okay, so parameter passing, that's it. The ampersand goes in the function definition if you want to pass by real reference, and there are no stars involved. And remember the const ref mechanism as a safe way for saving on copying and not having inadvertent changes. Just two more things about functions, default arguments. So if you define a function and the last argument, the last one or more arguments from the end, they can you can declare them like here, double y equals 0. Then that means that you can use the function with two arguments, and if you use it with one, then the missing one is filled in with the default argument. So with one argument, distance computes the distance to the origin, and with two arguments, it's distance between 2 points. For obvious reasons, default arguments should come last in the argument list. I often use this for the following, for the following reason. So I declare a function with a final parameter for tracing. And so if I write complicated functions where I may want to print out intermediate results. So yeah, so you call your function, and the cases where you think that it will go right, you do fine, and the cases where you want the intermediate output, you supply that Boolean parameter. So this sort of idioms I find useful. Another thing you can do in C++ is polymorphism, which means many shapes. So you can define the same function multiple different ways, and as long as the compiler can figure out which one you're using, it will invoke that one. So for instance, you can have an average of 2 and an average of 3 doubles. Okay. And because the compiler sees whether you call it with 2 or 3 arguments, then the compiler can figure out which one to use. Now, the compiler cannot figure out what you're using, or it is prohibited to have polymorphism only depending on the return type. So you can only distinguish them by the inputs. And there are some potential problems, potential pitfalls, but basically, especially if you distinguish functions by the number of arguments, then polymorphism can be a useful mechanism. Okay, we're getting to what you probably came here for, object-oriented programming. So, yeah, when Bjarne Stroustrup initially wrote C++, he called it C with classes. So it was C with an extra mechanism on top of it for having classes. Classes came out of a language called Simula 67, which was an Algol dialect, and probably the first language that looks object-oriented to us from a modern perspective. Object-oriented programming, classes. Okay, so classes look a little like structures in that they bundle data together, but you should not focus on the data aspect. An object is something you can ask to do something, so you should focus on the functional aspect of it. An object is an entity that you can request to do certain things. Those actions are called the methods, or function members, strictly speaking. And to make the methods possible, the object probably is storing data, which is known as data members or just members. But focus on the methods. When you're designing a class, ask yourself, what functionality do I want my objects to support? Now, to get the terminology straight, a class is like a user-defined type, and an object is an instance of that type. So you define your class once, and then you create multiple objects of that type. As a running example in this course, I will use a geometry-inspired classes. So points, lines, shapes in the plane. And so your program will look more or less like this. You define a class, point, all sorts of stuff, and then you do that outside of the main program. And then in the main program, you declare point P. So it's like point has become a new data type, like int, float, character. By having this class declaration, you can now declare variables of a type defined by you, namely a class type. Yeah, so we're going to be playing with points. And I said that the functionality is the most important thing. So what are the sort of actions that a point should be capable of? What do you want a point to do or return? Post something in Slack if you feel like it. If you're doing mathematics, what do you do with a point? Connect with other points, sure. So draw a line through them, or make a square or an object from them, sure. You have in fact already seen something in the slides. Return its location. Yeah, well, if I say 0.4, then that is its location, right? Points can return Cartesian coordinates. Okay, adding, subtracting points. Yes, so finding the connecting vector between 2 points. That's a good one. Obtain the distance between 2 points. Absolutely, yes. So those are a couple of good suggestions, and in fact, you will see them come in this lecture. Okay, so without saying how we're doing things, here are some illustrations of doing things with points. I make the point 1, 2, and in case you're wondering, 1 point, 1 dot is a double, it's not a float, but can of course be truncated to a float. So I make the point 1, 2, and then I okay, take a close look at line 3, P dot distance to origin. So if you would write this in C, you would say distance to origin and then P in parameters, which means you pass an object, the point object, to a function. Here you do it the other way around. So you say, okay, point P, what is your distance to the origin? Okay, so the function distance to origin is only defined in the context of a point, and it doesn't take any further arguments because you ask point, what is your distance? And there are no arguments to that question anymore. Line 5, you say, okay, point, scale yourself by 2. So, and then you print out again distance to the origin, and it's become twice as much. And on line 9, you also say, okay, what is your angle to the x-axis? And it gives you something in radians. Okay, so here you've seen a couple of methods of the point object in action. So distance to origin, which returns something, and scale by, which doesn't return anything, but it changes the state of the object. The important thing to see here is the dot notation. So object dot name of a method, and methods can have further arguments, and sometimes they don't. Okay, so here I've only focused on the functionality. What can you ask a point to do? Now, as I pointed out on the second sentence, to make these methods possible, the object probably needs to store some data. So if you want to ask a point, what is your distance to the origin? What data should it store? Is there more than one possibility? Post in Slack. What distance metric are we using? Cartesian. Well, distance is what is this? Distance. Cartesian. Is that the answer you were looking for? So what does a point need to store in order to compute the distance and the angle? Right? And in this code example, I'm saying, okay, point, what is your distance to the origin? What is your angle to the x-axis? No? Okay, the obvious one is if I say point 1, 2, I let the point remember its x and y coordinate. What is the non-obvious answer? See line 9. Place of origin, I'm not sure what you mean by that. If you mean where it's located, then that could be stored as two doubles, namely the x and the y coordinate. But line 9, I'm asking for the angle. So the second possibility is to store polar coordinates, right? Oh, Euclidean distance as opposed to Manhattan distance. Okay. So the obvious answer is store the x and y coordinate, and the non-obvious answer is store r theta, so polar coordinates. And note that my code that prints the distance to the origin works with both Cartesian and polar coordinates. So you need to bear in mind that implementation details, like what data is being stored, is completely decoupled from the API, which is that you're able to ask distances and angles. Okay, so API and implementation details are decoupled. Okay, what is the object workflow? You define a class, and you define both its data members and its methods. You do this typically in somewhere before the main, but separate compilation we'll get to later. Then you create objects, and note line 1, you may create it with some data, and then you ask your object to do various things. Okay, so this is the workflow. You define a class, you create objects, you do things with the objects. Okay, so what does a class definition look like? Well, first of all, the data members and the function methods. So it is a good practice to keep the data hidden, and you do that by saying private, and then you specify the data that is being stored in the object. So let's take the simple solution to how you create a point. You store its x and y coordinates. And then publicly, you have the API. Now, the first point of the API is, how do you create a point? So here you see that a point is being created from an x and a y coordinate. So I need to define how this goes. That is called a constructor. And so on line 5, you see that inside the point class, there is something that looks like a function, point of double, and then curly braces, it does something. So line 5 through 8, that is called a constructor, and that is the function that creates the point object. Now, it does not entirely look like a function because it doesn't have a return type. So that's how you actually recognize the constructor. It has the same name as the class, and it has no return type. And so what does this function do? You put an x and a y in it, and then those get copied to the x and the y that are stored as the data members. So this is often what a constructor does. It only copies the external data into the data members that are kept privately inside the point. Constructor. As I mentioned, a best practice is to keep your data private and to only expose the methods to the public. I usually first declare the data and then the methods, and there are just as many people that flip it around and that say, okay, first show me what the public methods are, and then towards the end I'll specify the data. It's a point of style. You can have them in any order. You can have multiple of these sections. Okay, so now the distance and angle functions, which are the function members or methods of the class. So you have your point class, and I'm skipping the stuff that the constructor and the data that is being stored, and I'm only focusing on that distance function. So inside your point class, you now define a function, and this looks like a classic function. It has a double return result, and it has a name, argument list, function definition in curly brackets. And so the distance function says return the square root of x squared plus y squared. Now, it looks like an ordinary function, but it uses that x and a y, and those come from the class. So inside a function method, the variables, the data members of the object act like global variables. So the function can use them without you having to pass them through the argument list. Now this function is defined with a name, but it cannot be used by itself because it's inside the class definition. You have to use that dot notation to use that function on an object in your main program or calling environment. Okay, so inside the class, you define a function, and then where you use the object, you have the object and you say, okay, object dot whatever you want me to do. Oh, did I mention this? So if you go to my website, then there is a public source repository. Let me post that in Slack. Okay, link is in Slack. So this is the public source repository in case you feel like formatting my book for yourself. Actually, I know of people that teach from my textbooks, and they appreciate that they have the source files of the book. But what you want to have is this skeletons directory, and you want point class.cxx, point class.cxx. So that this gives you a template code to work from. And I hope this is visible. Let me blow it up by a little. So this gives you the template code to work from. It's a point class. What was the question? Oh yes, add an angle function to this. We have only limited time. I'll save you this exercise. I'm sure you can sort of imagine how this goes. I want to do a more serious exercise in a minute. Anyway, but that's a repository, and that's where you can find the code templates in the skeletons directory. Yes, to the question of what distance we're using. Well, here you have the Manhattan distance. So yeah, if you want to do that exercise. Okay, let me yet again stress the point that stored data and the API are decoupled. So here is a example of a point class which stores the polar coordinates, so r and theta, but the constructor still uses x and y Cartesian coordinates, and so the constructor then converts it from x, y to r theta. Okay, so decouple API from implementation. Okay, so if you sometimes find Cartesian coordinates more convenient and sometimes polar, why not store them both? So that makes it very easy to print the angle, for instance. Does anyone see a problem with this design? Post some keywords in Slack if you have an objection to this. Or do you think that this is a great idea? I guess the answer to this would take a lot of typing. Feel free to unmute yourself and say something if you have an opinion. Yes, okay, so good answer. Inconsistent data between x, y, r theta if one changes. Yes. So there is redundancy here. The same information is reflected multiple times. And so if there is redundancy, then you have to worry about the two instances of the same information getting out of sync with each other. So this design is very dangerous. Right, inconsistent, redundant, do not repeat yourself, single responsibility. There are various keywords that you can throw out here. Yeah, so this is a bad idea. Do not store redundant data. Try as much as possible to store only the necessary data. And so if you are storing polar coordinates and you need the x coordinate, derive it with a sine cosine function. Yeah. Okay. So data in an object is private. Here's a exception to that rule. Different objects are able to access data. Objects, how should I say this? Let me just read from the slide. You can access data members of objects, other objects of the same type. Well, inside class methods. Okay, so suppose I have a point class, an x and a y, and I want to flip the x and y coordinates. Take a look at the flip function. So I have a point flipped, and I say, okay, the x of flipped is y of the point that I'm working on, and the y of the flipped point is the x of the original point. So this is an incomplete code example, and I'm not going to go further into it. But so if you're in a method and you are describing the interaction between 2 points of the same class, then you can actually access the data members of the other object. And you need that for the following exercise. So for this, I do want you to work for a couple minutes on this exercise. So clone my repository that I just posted, or cut and paste from the website. Take this point class and do this exercise. Write a method distance, which computes the distance between 2 points. Okay, this is very important for your understanding of how these objects work, and in particular, this mechanism. I'm setting a timer again for 6 minutes. By the way, if you're wondering about compilers, these days my favorite is GCC 12. That's the compiler that understands most of the modern features. While at TAC, we advocate the Intel compiler. Intel is kind of slow in catching up with the latest C++ standards. So it's only the latest Intel compilers that the one API suite that does that decently. So I do a lot of my testing on GCC 12. But what you're learning today is pretty bog standard, so any compiler can do that. But okay, exercise. How's everyone doing? Anyone stuck? Feel free to post solution, but try to cut and paste only the relevant function. Post correct solutions, post incorrect solutions. And I posted a second poll. Just curious, what's your workflow? I mean, I am old school, hardcore Emacs and compiler, actually Emacs and Makefile. But I see the attraction of things like VS Code, or if you're on Windows, VS Studio. Oh, I should have included an other option. There is NetBeans, Sea Lion. There's a couple of those commercial environments. Yes. To start with the question, is a method the same thing as a derived class? Nope, nope, nope. Derived classes we'll get to in a couple of minutes. That's an entirely different thing. Johnny, yes, that is a correct solution. So if you look at the line of code as how this function should be used, then you say point, what is your distance to another point, which means that the distance function gets only one argument because it is applied to a point, and so the first argument is sort of implicit. It's the object that you're working on, and so indeed the distance function has a signature of float distance 1 point argument, correct? And then you compute the delta x as x minus p comma p dot x. That is perfect because as I pointed out here, you can actually access the x and the y of the point p directly, and then you return the square root of power and power. Yep, very good. Let me just remark that a point object is a very tiny thing, but if you start writing this sort of stuff seriously, then you may want to contemplate float distance of const point ref p. So if your point object is big, the way you coded the solution, the other point gets copied in. For two floats, you don't care about it, but in general, passing it in by reference and then preventing it from being altered, so using const ref, is a good idea. Okay, let's continue. I appreciate that people work on the exercises. I would prefer teaching in person so that I can look over your shoulder and help you. Okay. Yeah, let's not do this. Okay, so now we've done, what did we do? Angle and distance, and those are all functional style methods. The data goes in and a result comes through the return parameter. Now, you can also do other things. You can write a method. What happens if you try to modify a const variable? The compiler complains. So yeah, using const is a great way of having the compiler check that you're not violating what you say you are going to be doing. So yeah, it's a way of catching potential mistakes. So if you say that something is constant, so conceptually from your algorithm, it is not going to be changed, and so you say it's constant, and then you try to change it. The compiler says, hey, there is a discrepancy between what you're saying and what you're doing, and so compiler error, yes. Would it error? The compiler catches this. So the C++ compiler can actually catch a whole bunch of things that would potentially be runtime errors or wrong output in the case of a C program. Okay, slide 36. You can change the internals of a point. So you can say point, scale yourself by something, and then you do that by multiplying the x and the y coordinate. So as an illustration, I create my point. I say distance to the origin is whatever, square root of 5. I scale the point by 2, and it becomes square root of 25. Right? So sometimes a method does not return a result, but it acts on the object itself. So you can scale a point, for instance. Okay, I need to go into a bunch of technicalities. So in this example, you had a constructor. Let's see, how did I do that in my sample code? Okay, in the skeleton code, yes, line 23, the data comes in and then the constructor copies it into the private data members. Now, there is a number of different ways you can do this, and there are some aspects to this that are worth discussing. So, for instance, you can have square root is used without being defined. Yeah, for cleanliness, you should probably include CMath. Let's see, did I do that? Yay, line 16 and 17. I am actually including CMath, but yeah, a couple of these math functions you can use without them being declared. And if you use Manhattan distance, you need to write your own function. So you could, okay, I'll not go further into this, but yeah. So note that in my skeleton code, line 16, 17, I am for cleanliness including CMath. Okay, you can have default values. So you can skip initializing them in the constructor, or you can even dispense with having a constructor. We'll get to that. So default values. Now, so the code that you've seen a couple times now has the constructor copying the data into the private data members. There is actually a different syntax for that, which is with a colon notation. And this is the first time probably ever the colon does not normally appear in C code unless in the ternary conditional. So this is a new notation. In between the argument list and the curly brackets for the definition, you can have initializers. And that is the preferred way for getting data into the data members. We'll get to probably, yeah, we'll get to why later, but I'm just pointing out to you that this exists, and trust me that this is the preferred way of doing it. So not copy it in the constructor, but use, this is called a member initializer list. So the data members get initialized with this colon notation. We'll get to the technicalities later. Interaction between objects. Let's see, what was this about? Let's see. So you have just seen the, where was it? The scale by method, which scales an object by altering the state. Here is a scale method which takes a point and then returns a scaled copy. So I'm giving you some different idioms for dealing with objects. So in your point class, you can have a method scale. And what does it return? It returns a point object. Kind of makes sense, right? Point is like a data type. A function can return a data type. So why can't a function return a point? So what happens here? You have a scale method. And so it's something you apply to a point. See line 12, P1 scale by something. But now it returns another point. And so that's why on line 3, the scale function has a return type of point. So a point was constructed from an x and a y. So on line 5, I have a point from the scaled x and the y coordinate. That makes sense. Oh, I'm feeding you maybe too many things at once. Line 4, scaled point is this new point, except that, so I'm creating a scaled point, and then in line 6, I'm saying return scaled point. You sort of see that, right? I'm creating a new point and I'm returning it, and so the function does what it's supposed to. But on line 4, what is that auto thing? Okay, this is a new thing in C++, and it is often very convenient. If the compiler knows what the type of a variable is, then you don't have to spell it out. So I could have written point, scale point is point, but because I'm using the point constructor, it's clear that scale point has to be a point, and so I don't have to spell it out. I can say auto. If the compiler can figure out what the type of a variable is, you don't have to spell it out. You can just write it there. And this really often, really simplifies code. It's a very cool mechanism. It's not quite Python, where you don't have to give where you don't have to specify types at all, but at least you can tell the compiler, you can figure out what type it is. Okay, so now you've seen that a function method can create a new object of the same type or of a different type. Okay. So in line 12, you've seen the syntax that you've seen once or twice before, that you say point P2 is whatever. So you use the type as an identifier, as a type identifier, and then a variable name stuff. But on line 5, you use the class name, and there is no identifier. You say class name and then the constructor arguments. So that's a different way of constructing a point. And so here are two code blocks. The left one is what you saw on the previous slide. You create a scaled point and then you return it. But on the right, why not create that point and immediately return it without ever involving a variable? Okay, and the right code block may have advantages because on the left, you first create a variable and then you return it, meaning that it gets copied to the variable in the main program. So you create an object and then you copy it. By using the block on the right, you are, and this is called move semantics and copy elision. So the C++ compiler can often eliminate unnecessary copies. And so by using this return statement, the point does not get created and then copied. It immediately gets put on the location where you put it in the main program. So be aware that this sort of, it looks like a shortcut. It is possible, legal, and it probably is better for performance. Okay, so that's to give you a whole bunch of idioms. Let's not do this one. So you've seen a couple of examples of a point method creating a new point. So you, if you want to check that you can do this sort of thing, you can, for instance, write a method halfway. And so now you have a point P, a point Q, and you say new point H is halfway between P and Q. I'm sure you can figure out how to write this. You can write this in one go, but maybe you think that halfway is a combination of adding 2 points and then dividing them. So you can actually write methods add, scale, and then say halfway is the scale by 2 of the add of those 2 points. Okay, so feel free to experiment with this. Oh, and of course, where in this slide I wrote P plus Q, that is metaphorical notation. But in C++, you can actually overload, as it's called. You can redefine the plus operator so that if you have two point objects, you can actually write P plus Q in your source. So you don't even have to use an add function. We'll get to that. But for now, writing P plus Q is metaphorical notation, and you would have a function named add that has the effect of adding them together. Okay, this exercise is pretty obvious if you understood the foregoing. Oh yes, Lauren said that you can always unmute yourself and ask questions. So post questions in Slack, or unmuting is allowed. Okay. The default values can be used to not have to use a default constructor. Okay. You have a couple of times now seen the constructor. So polymorphism, having multiple definitions of the same function, that also works for constructors. So you can have multiple constructors, and one of them is called the default constructor. So I need to say something about that. Here's a bit of code. So you make a point P1 and you create that, and then you say, okay, P2 is also a point, and I'm going to do that by scaling P1 by whatever. With the code that you have right now, this will give a compile error. For instance, GCC will say no matching function point. Huh? Point. Okay. first of all, it doesn't compile. Why doesn't it compile? Well, you only gave your point class a constructor that says, I can make a point from an X and a Y. And so the definition of P2 here is not legal because you're not giving it an X and a Y. The compiler error makes sense. First of all, point, : point means class point and then the function name point and then empty parentheses. So the compiler error said you try to, in your class point, call a constructor with empty argument lists. So it says there is no constructor with no arguments. And that makes sense because P2 looks like you should be calling a constructor, but there are no arguments. Okay, so the error message kind of makes sense. It's not entirely helpful if you're just starting, but it makes sense. Remember that the : notation is for class method. Okay, so what is the problem here? The problem is that you try to construct P2 without arguments, and you've only given it a constructor that has arguments. So P2 wants to use the default constructor, which is no arguments and don't do anything. But, and in this argument, you actually see that the default constructor exists by default. This code works. There is no constructor defined. So if you now create an object, it will use that default value on the one variable. So by default, there is a default constructor. And as soon as you write another constructor, the default constructor goes away and you can no longer write point P2 like that. Okay, two solutions. Use polymorphism and just say, okay, I have two constructors. If I say point without arguments, then use the default constructor. If I say point with an X and a Y, then use the other constructor. So that's a way to solve this problem. And now you can write this code. There is a different syntax. You can say, okay, point without arguments equals default. So use the default constructor and the other constructor exists. Okay, so if you want to be able to write point P1 with arguments, point P2 without arguments, then you need to have two different constructors. Someone is raising their hand.
Yes.
Unmute.
Can you hear me?
I can hear you, yes.
Okay, great. So for another way of calling the constructor without any argument, can you use a default argument value on the main constructor?
Ooh, that is close to becoming ambiguous. I'd have to try that out. Note that point P2 has no arguments. And if you wanted to use a default value, then maybe you'd have to use empty parentheses.
Right.
I don't know. I'll experiment with it.
Thank you.
I've never used a constructor with only a argument with a default value. I've used constructors with regular and default value arguments. Huh. Okay, interesting. I'll play with it. Okay. Let's see. This is this exercise. I guess this exercise sort of makes the point that in C, if you would write a linear function, you would give it 2 x's and 2 y coordinates. And in C++, you can make things so much more elegant by having levels of abstraction. So a linear function is not defined from 4 values, it's defined from 2 points. And so you would first create 2 points and then say, okay, now make a linear function through them. And then, for instance, that function would have a member function evaluate the function at whatever x coordinate. You can do that exercise when you get home. Okay. So when I teach this material in class, I let my students write a prime number generator. So objects can correspond to somewhat tangible things like a point. Even a function is fairly tangible, but the set of all prime numbers, that is a little more abstract, right? And the set of all prime numbers, how would you, what if you want to make that into an object? Obviously, you cannot store the whole thing internally because it's an infinite set. But you can ask, okay, what methods should it support? And the set of prime numbers, a logical thing to ask is, okay, what's the 10th prime number? Or a little more generally, you can ask it, okay, give me a prime number, give me a prime number, give me a prime number, and then you would ask that 10 times in a row. So, so let's look at a class that models something abstract, like a stream of data. This code models the set of integers. So you would remember what the last result was that you yielded. And so initially you set it to 0. And note on line 10 that I'm creating this object, but the class does not have a constructor, so it uses the default constructor and it uses the default value. Does anyone want to remark on line 3? You see something that you haven't seen before? And so this stream class has as its only method next. So you ask your stream, okay, what's your next number? What's your next number? What's your next number? And internally, it keeps track of what the last thing was that was coughed up. And then it increases that. Okay. And so every time you call next, you get the next number. Line 3. No one sees anything unusual. C++ has different ways of initializing data, and it gets a little confusing, but there is a good reason. No, there is a reason for not using equals. So you could have written int last result equals 0, but here I'm using the curly bracket notation. Which is another way of initializing variables. Prefer not to use Slack chat. Yeah. Yeah, yes and no. Okay, so this class models something abstract, the stream of integers, and now your exercise is make a prime number generator. Isn't there? I thought there was a skeleton for that. Yep, there is a stream.cxx, which is basically the previous thing. So write a function is prime, or did I? Yeah, we've been going for a while. I need a break, a little longer break. So I'm setting a timer for 15 minutes. So this is the official break. And if you want to work on something, you can use skeleton code stream and extend that into a prime number generator. -15 break till the top of the hour. Okay, Lauren, I don't know if you paused the recording, but you can roll again if you did so.
I did not. I'm
Okay,
just gonna edit.
works for me. Okay, did anyone work on this exercise? Feel like posting a bit of relevant code? I'm still sharing my second desktop, right? Yeah, probably. And if you were in my UT academic classes, you would then do a cute exercise about the Goldbach conjecture. This is actually a cool exercise. If you want to test yourself, try doing it and send me your code. There's always students that come up with kind of hackish solutions and ones that come up with an elegant solution. And yeah. Anyway. Okay. So maybe you found yourself at some point writing a function get x, which returns the x coordinate of a point, and that's called an accessor. And they're not always necessary. In fact, there are mechanisms. Okay, let's get one thing out of the way. In my the point definition here, the x and the y are declared private. If you declare them public, then you can suddenly access them from the outside world, and that is dangerous. So let's not do that. Let's try to limit how you can access data members. But you can do the following. Line 5, there's a method called xComponent, which returns x, but pay attention, the return type of that is a double reference. So it actually returns a reference to the internal x. And so in the main program, you now see that you can use that function xComponent, which gives you a reference to the internal data member, and now you can alter it. That is kind of weird, right? For a C programmer, it looks like you assign to a function, but because of the reference mechanism, this works. You can use this, but use it sparingly. Do you really want to assign to a data member, or for instance, in the case of a point class, and suppose you want to translate a point by whatever distance, that should not, in that case, you want to have a method called translate, and you don't want to say, well, translate is just add to the x, so I get the x and no, write a method translate. So think in abstraction levels. Okay, so here you return a reference to an internal data. Now, you don't yet know what a vector is. We'll get to that next. A vector is like an array. So suppose that you have a class grid, which has a big internal array, and you want to be able to read from it. In that case, you can have a method that returns a reference to that array, but it returns a const reference. So you get a direct access to that array, but you cannot alter it. So this const ref mechanism appears quite often in C++. It's an efficient way to have safe access to data. My point about not exposing internals to the outside is that your object is more than just a collection of data. There is often an invariant or a predicate on your data. For instance, suppose that you have an object point on the unit circle. You can store that as an X and a Y. Nothing wrong with that, but there is a restriction on the X and the Y. And so you want to prevent being able to alter just the X or the Y, because that would violate the invariant that your point is on the circle. So you can only say change my X and then the Y gets changed accordingly. Okay, so realize that an object is more than just the data. It's the data with some predicate on it. Const. Okay, this is advanced stuff. If for some reason inside an object you need that object, then it's accessible through a keyword called this. If you speak Python, it's like self, which is the first argument of a class method. In C++, it's implicit. You don't spell it out. So suppose you have your class, some class, and you have a function that works on a class. And now inside a method, you want to use that function. So how can you get hold of yourself? Well, that is through this. I'm not going into this. I'm just mentioning that it exists in case you come across it. Advanced topics, operator overloading. So all your arithmetic operators and things like assignment and square bracket, subscript, parentheses, invocation can all be redefined. And so in this example, you have your point class and you want to be able to multiply a point with a scalar, so to scale it. And you would do that by defining, okay, note that I'm using the double colon notation. So inside the point class, you have a method called operator star. It takes an argument. Well, in the definition, it takes an argument. So compare line 1, the definition that says that star takes an argument, and line 7, where you have a point and you multiply it with a number. So there are no parentheses there, but line 7 gets interpreted as a function call. Okay, so that way you can redefine multiplying a point, adding 2 points together. And like I said, you can redefine arithmetic operators, you can define assignment, you can define square brackets. So there's a whole bunch of possibilities there. It's a very nice mechanism, gives really nice readable code. Yeah, so if you did the halfway function, rewrite this with plus and times. I'm not going to go into this. Let me mention a couple more things that exist. So in C, if you had two quote-unquote arrays and call them X and Y, and you would say X equals Y, then that would be a pointer copy, but not a data copy. C++ is different. If you have an object, whether that's an array or a class or something, and you copy it, then the whole data gets copied. And that is done through something called the copy constructor. So a copy constructor is a function, but it makes the equals sign behave like complete copy. So in C, if you had a complicated structure and you wanted to copy it, you had to write a complicated copy routine, including the recursive copying. In C++, it's all done for you. As soon as you have any class, the equals operator does precisely what you want. It takes an object and makes a complete copy of it, recursively even. Okay, so as an illustration here, you have code. It's a class that is called hasInt because it only has an int. And on line 5, I define the constructor. So hasInt has a constructor, and what does the constructor do? It says I'm being constructed. And then on line 9, I have the copy constructor, which looks a little like the constructor because it has it's a function with the same name as the class, no return type, but it has one argument that is a reference to the same class, or maybe a const reference, or the couple of variants, but this is the simplest one. So that's called a copy constructor. It says if I give you an object, construct a new object of that type, and this one prints out that it does some copying, and it does the copying. Normally the copy constructor is defined by default for you, but here I'm redefining it so that you can see it in working. Okay, in action. I make a hasInt object which has a 5, and now this is one of the ways that you can use the copy constructor. I make another object from that object, and I print them out, and they both have the same thing. So copy constructor. Copying is recursive, I mentioned that. And finally, there's the copy constructor, there's the constructor, the copy constructor, and there is a destructor. So that is also a function that is defined by default, but you can redefine it. It is a function with a somewhat strange name of tilde, class name. And the destructor is called on an object going out of scope. So you have curly brackets, for instance, a branch of a conditional. Inside that you create an object, and then when you leave the conditional, that object should go away. If that object contains an array, you don't want to have a memory leak. You want that array to go away. Well, in C++, that is done automatically. If the object doesn't exist anymore because it's out of scope, then also all the memory gets released. So a big argument for using C++ is that memory leaks are basically impossible. For complicated codes, that's a very good thing. Okay, so that is done through the destructor, and normally you never see this in working, and I'm only pointing this out because as C programmers, you may wonder about memory leaks. If I teach this from scratch to someone who's never dealt with memory leaks, then you don't have to point this out. It's obvious. The name of the object doesn't exist anymore because you're out of scope, and the data doesn't exist anymore. That's what you expect. But in C, that's not necessarily what happens. Okay, destructor is defined by default. It makes things go the way they should go. Here's an example. The destructor says I'm being called, and you run an example and it does that. Study that at home. Headers and separate inclusion. Okay, so I'm assuming you know the .h mechanism of a file with only the function signatures, or technically the declarations. In C++, it's a little more complicated, unfortunately. So what did you put in your header file if you're writing classes? Unfortunately, in the header file, you pretty much put the whole class, and the only thing that, so the names, the private publics, all the data members, all the function names, the only thing that does not go into the header file is the actual definitions of the functions. So your header file has to spell out the whole layout of your class objects. And then only in the implementation file do you have the function bodies. So here you have that double colon notation that you've seen a couple times. In the header file, it says there is a something class with a some do function. And then in the implementation file, you spell out your function something colon some do, and then you blah, 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 blah. Okay. So that's how you do headers in C++. It's a little more complicated. And with that, you can do separate compilation the way you do it in C. You have your header file. You include it in your main file so that you can use the classes. You include it in your implementation file just for sanity, and then, okay. Yes, static variables. The traditional example being, if you create a bunch of objects, you want to count how many objects are you creating. And so you want to have a variable in your class that acts like there's only one of it. And so that's done with line 3, static inline. A variable that is declared like that acts like there is only one incarnation of that variable across all the objects. You can also have static functions, but I don't think I am. Yeah, you can also have static functions, but I don't discuss that here. Anyway, static variables typically used for things like counting how many objects you've created. Okay. Static variables are also good for having random number generators. You don't want to have a different random number generator in each object. So if you need a random number generator, you put it statically in your class. More object stuff. So you've seen the cout function. And out of the box, cout can only handle basic variables and strings. Now, what if you want to cout an object? Then this slide is sort of out of place. We'll get to that later. I'm not sure how it got there. Someone mentioned derived classes earlier, so that's what we're going to be doing now. So if you have multiple classes, one class can contain objects of another class. So course instructor, you have a person class, and then a course class would have a person class for the instructor. So that's a has-a relation. I mostly want to go into this, the is-a relation. So that is derived classes. You have two classes where the other, where one is a specialization of another. Since this is a TAC class, I'm assuming that everyone has some amount of numerical analysis in their baggage. You need that for doing computational science, right? So you may know what interpolation is. And so you write a general function interpolator class, which allows you to compute interpolated values. Okay, that's general, but then there are specialized interpolators like a Lagrange, Hermite, spline interpolator, and they all are a little different, but they all have this basic function of, okay, how much are you in this X value? Okay, so there's the base class function interpolator, and then there are derived classes that differ, for instance, in what data they store. Okay, so base class has a certain functionality, and then the derived classes can differ in what methods they offer, but they all support the functionality of the base class, namely, what is your value at some X point? Okay, how is this done in C++? Okay, you have a base class, general. That's a general case, and it has data, and it has a method. And note on line 2 that I'm using protected, which is like private, except that derived classes can get at the data. So the outside world cannot get it. It's not public, but it's private and accessible to derived classes. So my base class general has data and a method. And now I have a derived class special, which can have methods of its own. Oh, and it can use the general method. I should have had that. But at least in line 10, you see that the derived class has access to the variable of the base class. Okay, so the derived class adds new methods or has certain restrictions. It's a specialized case of the base class. Let me point out, how do you indicate that something is a derived class? Well, that's line 8. You say class special colon public general. So that means that don't worry about the public keyword. Private is possible here, but and that's pretty exceptional. So class special comes from a public base class general. So this colon notation now indicates inheritance. Where did you see the colon notation before? It had a slightly different meaning there. Post in Slack if you still remember that. Okay, so colon notation indicates inheritance. And now you have your special object, which can call both the general method and the special method. It's a special object, so it has the special method, but because it derives from the general class, it also has the general method. Now, one thing I didn't indicate in this example is how the derived class and the base class are constructed. That's another place where the colon notation comes in. So you have your general class, and let's say that the general class is constructed from 2 doubles, and the special case is where the 2 doubles have a relation, as in one is one more than the other. So the general class has a constructor, and now your derived class, so on line 5 it says special is derived from general, and on line 7 it says that the constructor of special, colon notation, so it calls the constructor of the general class with x and x plus 1. So the derived class comes from one parameter, which corresponds to the general case having two parameters that are one apart. Okay, so the derived class constructor has to call the base class constructor. If you don't do that, it will do the default constructor, which may be the right thing and it may not be, but typically you call the base class constructor with some arguments. Okay, so that's inheritance. Inheritance is tricky. Some people think it's evil. Some people think it's essential to object-oriented programming. I have uses for it, and oftentimes I don't use it. I already pointed out private, public, and protected. Oh, we didn't do this exercise about rectangle. No, we have limited time today. So this is a good exercise to do at home. So write a rectangle class. In fact, it's an axis-parallel rectangle, so it's parallel to the x and the y axes. A rectangle is defined from 2 points, the bottom left and the top right. Where is that exercise? Did we see that? I need to revise these slides anyway for next week, so I'll make sure that it's there. So in some exercise, you created a rectangle class, and now as a special case of that, you make a square class, which is a rectangle with it. Okay, good exercise to do at home. Yeah, this is, I really want to get to this topic, vectors, as a replacement for C arrays, both the ones that you create with square brackets and the ones that you malloc. This is way better. I'll remove that previous slide. C++ vectors are better than C arrays. So you've seen the keyword vector once appear on a slide. So the vector is not a mathematical vector, it's an array. Vectors are fancy arrays. They are easier and safer to use. For instance, they know what their size is. In C, anytime you passed an array into a function, you had to pass the length. What happens if you, well, at least the ones that you pass from a malloced thingamy. If you malloc an array and then you call size of in the function, what do you get? Not what you expect. Anyway, so C++ vectors know what their size is. You don't have to pass the size to a function. They can do bound checking. So they know what their first and last argument is. And if you index outside of that, it can throw an error. They do this destructor thingamy that I pointed out later. So if you create an array inside a function, when you leave the function, the array gets deallocated. So no memory leaks. And there's even dynamic behavior, like you can create an array and then add elements to it. Basically, in C++, you never have to malloc. If you happen to know that C++ has the new keyword as an easier malloc, again, you don't have to use, you almost never have to use that. So in 99% of the cases, use vector to create an array. I'll just mention that C arrays suffer from what's called pointer decay. Yeah, so that makes them very, very difficult to deal with. C++ vectors are just as efficient because under the hood, of course, there is a malloc array, but they have an easier interface. So don't use malloc, and if you happen to know about new, don't use that either. Okay, let's create some vectors. What do you need for creating vectors? You need to do include vector and then using standard vector. And now all of a sudden the keyword vector is defined and you can create arrays. Line 5 and 6, vector of int, vector of float. So this is the first time you see the the angle bracket notation. That's called templates, and we'll get to that next week. In C++, it acts like a vector is parameterized two ways, namely how many of what type. And the type of a vector is indicated with those angle brackets. So you say vector of int, and then you give it, so it acts like a compound type identifier, vector of int, and then you say its name is this, and then you either indicate of how big it is, or you indicate explicitly what's in it. So on this slide, you see examples of where you explicitly enumerate the elements in an array, and so you don't have to tell it how long it is because the compiler can count that. Vector of int, there's a couple of ints, vector of float. It's a vector of float, but 0.5 is actually a double. So the compiler or the compiler will convert that for you. Remember the auto keyword from, I said that if the compiler can deduce the type, it will fill it in for you. So in line 7, 0.5f is a float, 1.5f is a float, 2.5f is a float. And so the compiler thinks, okay, that's a vector of floats, and so it will fill it in for you. Okay, you can use square brackets as with C arrays, but there's also the function add, which also does indexing. That's line 8. So the line 8, the add notation, is here used to get the value, but you can also use that as a left-hand side. So you can assign to evens at 0 equals, and that's what this exercise will make you do. Okay. In C, if you needed to go over an array, you had to say for I is 0 to length -1, I++, and then you index that array. And there is a philosophical problem with that. Namely, if you are only interested in the values because you want to add them together, or you want to find the maximum value, you don't need that index. So why does C force you to do that index? You don't need the index, you only want the values. So for that sort of cases, C++ has a new notation which uses the colon again. So for float E in my data, that means my data is a vector of floats, and now I say for every value of E in that array, do something with E. And this gives you the values. So you don't need the index, you don't get the index. Okay? And again, because of the definition of my data as a float something, because my data has been defined as a vector of float, the compiler can figure out that E has to be a float, and so you don't have to specify that, and you say for auto E in my data, and now E successively takes on all the values in the array. There are various questions that you could now have. We'll get to all of them in turn. Okay, so a little bit of code. Vector of int numbers is something, and you want to find the maximum number, so you initialize your temporary max to something very negative. How would you do that more elegantly? And then you say, okay, for v is any value in the numbers array. If v is more than temp max, then temp max is v. And then you print out the temp max. Okay, so you don't need the index. You don't particularly care that the array is traversed increasingly, although it is. And so you're only interested in the values, and so this range-based for loop is a simple way of expressing that. This is the idiomatic modern C++ way of going through an array in cases where you don't care about the index. And in C++20, this will become even more crucial and useful. Exercise 18, you can do that if you want to test, you can do this. Okay, now this range-based for loop is great if you don't need the index, but sometimes you do need the index. So ask yourself, what kind of a loop do I have? So here are two examples. Count how many elements of a vector are 0. Can you do that with a range-based loop? Find the location of the last 0. Can you do that with a range-based loop? Respective answers are yes and no. Agree? So you may still need the index. This is a surprisingly useful thing. If you want to index over a short array, and you can give the indices, then you can actually, you don't have to create the vector, you can just put it in a for loop. So I find myself writing this surprisingly often. So for I in 2, 3, 5, 7, 9, it does the obvious thing. So in a number of places, you can use the curly bracket notation, which here you use to initialize an array, but you can also use it as the array itself. Okay, let's talk long arrays. So include vector using standard vector. If you say vector of whatever type name, it creates a vector of that type of size 0. If you create a vector of type with one parameter, size, it will create a vector. And unlike in C, where you malloc and you basically get randomly initialized memory, here the array is initialized to 0. If you want to initialize it to something else, then line 6 is syntax for a vector of a certain size and everything initialized to a certain value. So those are the more common ways of creating a vector that will potentially be large. Okay, now there are two ways of accessing vector elements. There is the square bracket notation, and you can use that both to get the value and to set the value. And then there is the add notation, which does exactly the same thing. Now, the difference is that the square bracket notation uses ordinary C pointer arithmetic, and so there's nothing keeping you from accessing data outside your array. It's not a good idea, but no one complains. If you use the add notation, then bound checking is done. Bound checking has a certain cost, and so this will be slower, but it's also safer. So what I tell my students in the beginning is, since initially you're not concerned about performance, use the add notation throughout. That saves you so much debugging. As an illustration, here is a vector of size 2, and I tinker, so it has indexes 0 and 1, and I tinker with elements -1 and 2, and nothing happens. It's kind of interesting to write a code and to see how far you can go outside of an array before something actually happens. That is usually hundreds of locations, and then you get a segmentation fault or so. Of course, if you do this, you may overwrite some other data, so it's not a good idea, but your program does not crash immediately. It just probably gives the wrong output. So the add mechanism is a lot safer. And if you try, if you exceed the bounds of your array, look at the output. It says terminating the program with an uncaught exception of type out of range. Yay. Okay. There you know, you stepped out of range. Where did you do that? Okay, we'll get to that later. It's a little harder to detect that. But at least as soon as you step outside of your array, the runtime system will catch it and say, okay, don't do this. Okay, so with the range-based notation, there's now a technicality. The variable I becomes a copy of the array elements. And so you can sorry, I can't find the code example I'm looking for. So if you're ranging over an array, then the variable becomes a copy of the array value. And so if you change that variable, that's allowed, but it has no effect on the array. If you want to range over an array and, for instance, multiply every element by 2, you use the reference notation. So you say for auto reference E, meaning E becomes successively a reference to every array element, you do something with E. And this code illustrates that. I create an array that contains 1, 1, 2, 2, 3, 3. I multiply every element by 3, and then I get the last element. And lo and behold, it is 6.6. So use the reference notation to be able to access the array elements directly. If your array contains objects of some big type, then again, you don't want to have them be copied, and so you want them passed by reference, but you want to be prevented from altering them. So yet another location where the const ref idiom makes sense. If you do need the index, for instance, you want to find not just the maximum value in an array, but you want to find where it occurred, then you can still use your old-fashioned indexing. And now you use the useful fact in line 3 that your array knows how big it is. So you can ask, okay, array, what is your size? And so you get that. So vectors are objects and they have a bunch of methods. So they had the add method for indexing. They have the size method for querying what is your size. And there is a bunch more methods. Yeah, let's not do the exercises. Oh, this exercise. Yeah, this exercise is useful for doing at home. So create a vector of floats, compute the norm of the vector, and then scale the whole vector by that norm, and then compute the norm again. And now, of course, the norm should be 1. That's a cute exercise to do at home. Vectors are objects, and I made the point that the copy constructor is recursive. So if you have 2 vectors, so vector of float v and v copy, and then in line 3 you say v copy equals v, then all the data gets copied. This code illustrates that. So making a copy of an array suddenly becomes a lot easier than it was in C. It's also a little dangerous because making a copy means that the memory demand goes up. But at least if you want this, it's possible. Let's see, vector methods. Okay, a vector is an object, and so you've seen at and size. There are many other methods. So front and back means get me the value of the first, value of the last element. Empty is a predicate that says, is your size 0? And later you will see methods that are dynamic. So insert an element in the array, erase an element from the array, which means shrink it. Yeah, so just to drive the point home, vector is a templated class, and so if you write, so it is as if there is separate code in the standard library for, there is a vector of int which has a size method, there is a vector of float which has a size method. The actual mechanism is a little more complicated, and we'll get to that later. Okay, vectors are dynamic, so you can extend them. There is the pushback function. So I have a vector 5,2. What does that mean? Does anyone remember from 5 or 6 slides ago? What does this declaration syntax mean? Is anyone still awake? Is anyone still keeping up with me?
Initialize a vector of 5 elements with R values of 2.
That's precisely correct. Yes, the first argument 5 is the length, and the second argument, yes, thank you for the reply in Slack. That is correct. Yeah, length 5, every element initialized to 2. And so on line 2, I push back 35, which means push to the back the value of 35, and now the size becomes 6, and back is the last element, which is 35. There's a bunch more functions. There is pop back, which means remove the last element. There is insert, erase. Now, if you were programming C and you wanted to add an element to the end of the array, what did you have to do? You have to malloc a larger array, copy everything over, put that element, and then delete the original array. And of course, C++ runs on the same computer that C does, and so it has the same memory. And so if you do pushback in C++, it also does the same thing of reallocating and copying. It's a little smarter. It will probably over allocate so that if you push back a number of times in a row, it is not going to malloc and free every time. So it's a little smarter, but still it has to do the same thing ultimately. So this flexibility is great for ease of programming, but be aware that it may come with a price. So here's an illustration. If you know the size of a vector, then I would say create the vector with that size and then set the elements. If you don't know what the size of a vector is going to be, create it with size 0 and push elements onto it. But only use that pushback method if you actually need that flexibility. Okay, if it's a vector of very complicated objects, then the pushback means that the object gets created only once. So there are cases where you have but basically in scientific computing, where most of your vectors are of fairly simple numeric things, create the whole thing in one go and then set the values. So don't use pushback. Here's an illustration of different ways of filling in a vector and timing it. And yeah, so the pushback method can be 8 times slower or so. So yeah, it comes with a price. Vectors and functions. Vectors are objects. You saw how you can have functions and object methods that yield an object. So you can have a method that yields that returns a function. So here's a function called make vector. You give it an int, it gives you a vector of that length. So the vector as a return result. You can pass a vector as an argument to a function and the whole story. So here's where the story about pass by value and pass by reference and const reference becomes relevant. You can pass a vector into a function, but if it's a long vector, you may not want to copy the whole thing. So you give it by reference, and then you give it by const reference if you only need the values, if you're not going to change it. Pass by value, pass by reference, pass by const reference. What is this exercise? You can do all these exercises at home if you want to change it. If this was a 1 semester course, I would assign a bunch of them to you, or we do them in class, but we have limited time here. So to conclude today's lecture, a couple of things about combining classes and vectors. So you have a class, a named vector field, and it has a vector of doubles with your values, and it has a string, a name. And now a question becomes of, if you call a constructor, when does that vector actually get made? And so this is one of those cases where, let's take a look at the second code block. You would call a constructor and you would call a constructor, and in the constructor you create the values. Now this means that first, when the constructor is called, it creates the memory for the objects, and then in the constructor body it creates a vector and it puts it there. So the vector object gets created twice. This is not elegant and maybe not efficient. And so this is one of those cases where the member initializer syntax with the colon is useful. So take a look at the first code block. Line 6, the constructor. I notice that there is an error, n elements and n should be the same. So you call the constructor with a name and a number of elements, and then you initialize the string name with name, and you immediately initialize the values vector with a vector, and this creates the vector only once and puts it immediately into the object. So you can use the constructor to create stuff inside the curly brackets, but what you can do in the member initializer list, that is better. So try to use that syntax. Okay. Vectors are one-dimensional. Multi-dimensional arrays, yes, C is just not made for scientific computing, and it's basically slowly catching up to Fortran 90 or so. How would you do multi-dimensional arrays? Well, you could create a vector of floats, that is and you call it a row, and then you make a vector of floats, and so you say 10 times a copy of row. This vector of something is not the right way to do a multi-dimensional array for performance reasons, because it will scatter your data through memory. You really want a matrix to be a contiguous block in memory, and this doesn't do that. So while you can write a matrix class, and you sort of have to write a matrix class because C++ only has one-dimensional vectors, you could write a matrix class and say, okay, it stores a vector, and my constructor creates that thing. And then I have a set and a get method or something. You can do better than this, but basically, this is not the best way to do it. The better design is to not have a vector of double, but you have to have a vector of double, that is the elements, and then you would create a long enough vector in the constructor, but then in the get and the set functions, you use this conversion formula, line 12, that if you index with I and j, you convert that to a one-dimensional indexing of I times the number of columns plus j, so that the API looks like you're two-dimensionally indexing, but under the hood, you're using this one-dimensional vector. Okay, so with C++ 17, this is about the best you can do, and this is it's a pretty good way of making your matrix classes. So yes, you have to write your own matrix class, but it's not too much work, and it gives a nice, elegant API. Oh, nice exercise. Do a Pascal's triangle. And so Pascal's triangle is a triangle. So you can use two-dimensional indexing and convert that to indexing in a triangle. So you store a one-dimensional vector of your triangle, and you can be more elegant. So it's a cute exercise. If you do one exercise at home today, try doing this one. And I have one method, 1 minute to, in these dimensions. Okay, C++ 17 had span. I think it had span. No, C++ 20 had span, which is a mechanism for having subarrays, which is very useful in linear algebra. And then C++ 23 has something called MD-span, and that is a true solution to the multidimensional indexing problem. So, yay. C++ 23 is with at least 23 years distance, no, 33 years distance, catching up to Fortran 90. Okay, C++ just doesn't come from a scientific computing world, but yeah, you can write your own matrix classes. So feel free to do that exercise at home. And that's it. It's 12 o'clock, lunch. Any questions remaining that I need to answer? Post in Slack or unmute yourself. Okay, in that case, thank you very much. Lauren, you can connect the recording. And next week,